What's up, YouTube? It's MR2. I want to take a look at some more motion. Today we're going to look at vibration, actually how it interacts with medium such as water. You can actually do this with any kind of thing, sand or sugar or anything like that, any type of loose granular medium that works in fluid dynamics. You probably can't see this. I'll post a screen capture or something of it. This is a tone generator. It just produces a tone through a speaker wire. It from 1 hertz all the way up almost, well, through 20,000. So, you know, this will make any sound pretty much we need in the range that people can hear. And what I want to show everybody is how that reacts with water. And most of you already know all this. Never mind her. And most of you already know all this. But I just want to go over a few things for people that don't understand how a speaker actually works. You know, wire comes from, you know, a source. This is speaker wire from my computer going to a speaker box. And there's 2 speakers in there, a little bitty one and a big one. But at any rate, they all work the same way. Inside this is a ring magnet, and inside there's a coil of copper that's connected to this this paper cone. And I tore this is all broken anyways. So you can see that how this moves up and also down. And if you put the electric current through this wire in the presence of that magnetic field, we all know what happens. The right-hand rule takes over, and it causes the coil to jump either back or forward, depending on which way the electricity flows through the wire. If it flows one way, it jumps one way. If it flows this way, it jumps the opposite direction. And that's basics of a speaker. What you're actually hearing is the actual pulse of the current that causes that copper to move, and that creates a sound. And this is only an up and down motion. So what we're about to see is just one range of motion, up and down. There's no side to side, X or Y. It's just the Z axis. And of course there's no rotation involved. And I'll get to that one of these days, hopefully. And what I set up here, we'll switch over to this camera now. Let's see so you can see that. Probably can't see it with that. I just put this camera over a little tiny drop of water on the table there. And we'll go to that camera. And turn on the generator now. I got it on square wave, and we're going to be doing the test with the sine wave. But at 1 hertz, you can't hear that in a sine wave. It's too gradual. So at 1 hertz on a square wave, we'll listen to, and you'll hear that's just one, you know, that's 1 hertz per second is what the timing of hertz is. And we're going to switch this over to sine wave and get it to an audible level, which is around 40. It can barely be heard. You probably can't hear it, but I can. And you can see that the water's moving. If I turn the volume up more. And we'll notice through the experiment that the volume has very little to do with what shows up in the medium. And we'll just incrementally go up. This is 39 hertz. Now it's at 41. And what really starts happening is through beyond 50. This is 46, 49, 52, 55. And we're going to begin to see here in just a few minutes as we cross over 60. This is 58. And a pattern begins to show up. And the higher the frequency that we go through, the more complex the pattern seems to be. In fact, you'll see how vibration, you know, takes one object such as this, and slowly but surely divides it into 2. And as we keep going, this is 73 hertz. As we start to get into higher ranges, we get more complex shapes. And you'll see here in just a minute that scalable type of deal too. It's different at scale. Scales are different, and that's probably because of the size of the molecule itself, I would assume. And of course, there's a resonant frequency in the plastic on top of this. It's going to have something to do with the outcome of any of your tests. This is at 87. We're fixing to go to. This is at 92. Let's turn it down a little bit because it does get too loud. You can't hear what I'm saying. And again, we'll go to 98. And again, we'll start out here at around, that's 48 hertz. You'll see let me turn the volume down. Because this begins to show up more like what we see in our weather patterns. You see how that shows up? The straight lines go across the, let's see if you can see that. As I turn the volume up and down, you can see how these things shoot out in straight lines. And of course, then you have a grouping of more like a circular waveform in the center of this. As we increase this, we'll see what happens. This is at 59 hertz. We'll go on through Q. And you'll see what happens as we get further and further along. 60, 69, 60, 64, 67, 71, 76. We're going to watch here as it gets higher. As again, the shape gets more complex. It goes from 1, and now you see that at the ends, 2 circular waveforms are showing up towards the outer edges of the sheet. Now there are 3 defined circular waveforms. And of course, if that whole table was rotating, it would, positive, it would resemble what we see in our weather. Another thing to note is the underlying patterns in the center, the smaller waves, the yin and yang patterns that show up in the center of these. You'll see it goes back to 2 again. 1, that's going to be so loud you can't see it. At any rate, I thought I'd show that to everybody. It kind of shows you how electricity and motion create sound, and just that one movement can be responsible for quite a bit of change. So I hope that helps. Peace and love. Big heads up.